So one of our last videos of the type 2 carbonyls, which concern aldehydes and ketones, is the Wittig reaction. Now, I say Wittig, but if I wanted to be prim and proper, I probably should say Wittig. So Wittig reaction is going to be very simple, just like the Wolff-Kishner reaction. So with the Wolff-Kishner and the Wittig, well, we're looking at a reaction that concerns the carbonyl bond of the carbonyl molecule. And that's pretty much it. So here I'm going to give you an overall story. And with that overall story, folks, I want you to then pay special attention to the mechanism that I'll show you afterward. All right, so here's the thing. We are going to take an aldehyde or a ketone, and here I'm going to write just an R or an H like we have had before. And what we're going to do is a reaction, and we have to understand what reagents will make this reaction work. And in the end, what will happen is that we will have our ketone or our aldehyde, and we are going to the oxygen, and we're going to replace it with an R group. And that R group is going to come from the reagent that we're going to add into the mix. So the Wolff-Kishner destroys the carbonyl altogether, and only hydrogens go on into its place. And then with the Wittig, or the Wittig, this reaction will look at the double bond of the carbonyl, and it replaces the oxygen with a alkene functional group. And this allows us to synthesize an alkene as a product. Just another way to make an alkene. And we've talked about ways to make an alkene back in Organic 1. And we did that by first starting the discussion off with an alkyne, with a YNE ending. And we said that alkynes, YNEs, can make alkenes with an ENE as long as we have the right reagents in order to make it go forward. So we take this triple bond and we destroy it to a double. Okay, well, the Wittig, or the Wittig, is going to require some reagents here. And this reagent is a specialized reagent that makes this go forward. And this is going to be called a phosphorus ylide. Now, some people say ylide, some people say ylide. The reason that they would say ylide is because they think of YL as in alkyne, ylide. But there's really more to the story than that. That's kind of misleading. But a phosphorus ylide is what's going to be required to make this product. So what's an ylide? It's basically a carbon that is negative, but it is attached to a bigger molecule that is maybe positive. So we see full-blown charges here. And the carbon has a negative charge on it, and it's connected to a larger molecule that has a positive charge on it. So overall, the molecule is negative, or neutral. The negative and the positive cancel each other out. But this is kind of particular because the Y in the ylide, or ylide, is the negative piece of the carbon, and a positive piece of the bigger molecule loves to hang out with the carbonyl. Okay, so let me kind of show you what goes on. Here we have a aldehyde or a ketone. And we've talked about the chemistry of this carbonyl, haven't we? We said that the oxygen's electron greedy, and it wants and wants and wants and wants and wants, and it sucks electrons up. So this is partial negative, and this is partial positive. So if we bring in this weird little thing called a phosphorus ylide, or ylide, then what we are actually doing here is that we're bringing a reagent in that has a carbon that is carrying a negative charge. And this negative charged carbon is attracted to that carbon that is slightly positive. Well, this carbon is attached to a bigger part of a molecule. A bigger piece comes along with it. And that piece is going to be a phosphorus-containing piece, which is a P. And that P has with it some buddies to the club. And what it brings are C6H5 groups. And there's 3 of them, folks. What is C6H5? You should know this. C6H5 are benzene rings. So here we are morphing all of these lecture topics all over again. So we are bringing in a phosphorus-containing molecule. That phosphorus-containing molecule has 3 benzene rings that are attached to it. And this phosphorus, because it's also attached to a carbon, and this kind of overwhelms it in a way, this is going to be a positive containing phosphorus. So we see this negative oxygen, right? Electronegative, partially negative, attracted to the phosphorus because it's positive. And we see the ylide part, the carbon that's negative, attracted to the partial positive carbon of the carbonyl. So it's kind of like a couple goes into a bar and we have just introduced 2 components that are attracted to each one of them. And one has the attention of the carbon and the other one has the attention of the oxygen. And we see this cyclic mechanism take place. So the cyclic mechanism, folks, this is a cycloaddition reaction. And this you have seen before. You've seen cycloaddition mechanisms. And this was with a Diels-Alder reaction that maybe happened back in the day of Organic 1. So this is basically a way for us to say oxygen is in a reaction, the carbon is in a reaction. This mechanism is taking place all at one time. And look at kind of what happens here. We form almost this cyclobutyl type of group when that begins to hang out and react. All right, so what happens here in the reaction? I'm not going to draw another step. I could, but I'm not going to. Is that this bond between the carbon and the oxygen breaks, as you would imagine. And this oxygen says, ooh, partial positive or full-blown positive phosphorus. Why, yeah, I want to hang out with you. Take me home. And we see a bond that forms right there. And this phosphorus says, well, you know, I can't take that many bonds. So what I'm going to have to do is I'm going to have to look at this negative carbon that's been holding me back. And I'm going to have to say, carbon, you got to go. We've got a life to live. And if this is what you want to do, it just doesn't work for me. And we're just going to have to end it. So break that double bond or single bond. So now this carbon, this poor little carbon that's right here, well, that poor little carbon does have somewhere to go because it had the eye on the partial positive carbon of the carbonyl. So what we actually see here are these electrons that basically are used in order to form that extra bond between those carbons right there. So that satisfies this negative piece. And that is the addition of our alkyl group. Okay, so that addition of the alkyl group is going to be pretty important. Right there it is. But here, carbon and this oxygen, folks, it still has an attachment here, right? I mean, this carbon and this oxygen are still attached to each other. So this is not going to fly. You know, this carbon, 1, 2, 3, 4 bonds. This oxygen has 2 bonds. It looks like everything is pretty much taken care of for the most part. But the problem here are these big, huge buddies that are coming with the phosphorus. These are 3 benzene rings. And those 3 benzene rings take up a lot of space. They need room. And right now, there is no room. It's too much for cover. You know, it's kind of like cramming 4 or 5 people into a phone booth when phone booths were still around. It's just not going to work. So oxygen has to make phosphorus happy. And phosphorus looks at oxygen and says, listen, if you want this to work, if you want to bond with me, then you're going to have to kick carbon away too. Because right now there's no room for me. You can't have me and that carbon at the same time. And the reason is because I'm not going to let my buddies go. I mean, these buddies have had my back the entire time. And I'm not going to choose between them and you. So if you want this to work, then you're coming with me, and I want to have you and these buddies too at the same time. But that means that you're going to have to just get rid of all of your past. Just get rid of all of it. So that oxygen says, okay, fine. I think we'll work out. I think we'll be fine together. I think we'll be happy together. So because of that, there goes that bond. Now, in the meantime, carbon says, I've just cleaved the bond to that carbon. So oxygen's going to come in and form that extra bond with that phosphorus-containing piece so it can be happy. And now this goes away, and we have this carbon that is now part of a longer carbon chain. All right, so if you want to kind of clean that diagram up, here's what we would call the short mechanism. So this carbon with a negative charge is attracted to the carbon of the carbonyl. The double bond carbonyl bond, the acyl bond, is attracted to the partial positive carbon. We see a cyclic mechanism that takes place all at one time. And this double bond's destroyed. And this carbon hooks up with that one. And that's what you see here. These 4 bonds that are right there, all drawn together. But phosphorus does not like this because of the 3 benzene rings. It's very large, it's very big, it's very fat, there's no room. So the oxygen has to break that bond. The phosphorus has to break the bond that it had to the carbon. So that way these 2 things can split off. And we see the O and the P run off together, happily in love. And this bond goes down to here, forming a double bond between those 2 carbons at this point. And this has created our alkene that we have talked about in the general template of the Wittig reaction. All right. Now, I want to talk a little bit about the ylide. All right. So here, where do the ylides come from? So C6H5, we said there were 3 of these on a phosphorus that's positive, and that's connected to a carbon, maybe like a CH2, that is a negative. All right, well, where do those come from? Well, those normally come from pieces that we use in a laboratory, and these are phosphoruses with double bonds between the P and the C. So this basically goes back and forth. And I really should draw an arrow that goes both ways here, because we see the ylide, which is over on the left, which is the positive and the negative together on the molecule. And it will flip-flop back and forth between the alkene version. It's not really a true alkene, but a double-bonded version. A double-bonded version back to the ylide, back to the double bond, back to the ylide, back to the double bond, back to the ylide, back to the double bond. And it goes back and forth this way. So in these reactions, they're very simple. You know what's going to happen because this is what they're going to do to you. They're going to say, hey, we've got this ketone, and I'm just going to draw it this way to the side, double bond O. And we are going to react this with C6H5, 3P, double bond, CH, CH2. And we want to know what forms. What kind of product would you get from this reaction? And a lot of people freak out because they look at this and say, oh, that's a ketone and that's not very simple. And now you're bringing in this reagent that looks even more complicated. I have no clue what kind of product. Yeah, you do. Let me show you how easy this is. You're going to look at this Wittig reaction, or Wittig reaction, and you're going to chop off the oxygen, and you're going to chop off the alkyl group, and you just switch them. That's all you do. You just switch those two pieces, and you've got the products of the Wittig. So basically what that means is that product number 1, CH3, CH2, that goes to this carbon that also has another ethyl group on this side, because we did a ethyl-ethyl ketone. And instead of the double bond O, this is now a double bond CH-CH2. That is what's going to go there. There you go, folks. That's all there is to it. And then the other part of this product, if you had to draw it, would be the C6H5 piece. There's 3 of them. That has a phosphorus. Now remember that phosphorus had a double bond here as well. So there's the double bond. It's still there. And now this phosphorus has paired up with that oxygen of the carbonyl. So this is our second product that we are really, for the most part, not interested in. So the organic piece is up there at the top. Now I can go through and I can name this organic. We have formed an alkene here. So the longest carbon chain, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, that includes the double bond. So it's probably either going to go this way or down. It doesn't matter. You'll get the same answer. So a 5 carbon piece is going to be a pentene, because this is a double bond. It's an alkene, and you should have learned that back in Organic 1. All right, well, it's going to be a 1, 2, 3, 1, 2, well, no, it's not going to be the same, is it? So I've got to be really careful how I number these. So a 1, 2, 3 from the left, or a 1, 2 from the right. So I'm going to give the double bond a priority. That's how I'm naming the group. So carbon number 1, carbon number 2, carbon 3, carbon 4, carbon 5. So at carbon number 2 is where my double bond is located. And then at carbon number 3, I have a ethyl group. So 3-ethyl, 2-pentene is going to be the product of this reaction. All right? So that's how you will handle the Wittig reactions. Again, they're very simple. They need to be simple. You shouldn't think about these too much. Chop the double bond O, chop the double bond alkyl, and play the game of switcheroo. You switch the two groups, and that's all you have to do. All right? Okay, so let's do one more of these examples. Let's do a ring, because we've not used those really, right? So here's a ring with a double bond O, and I'm reacting this with C6H5 3P, double bond carbon, and I'm going to draw this piece a little differently, all right? So CH3 on top and CH3 on the bottom. We want to know what product is going to be formed. Again, very easy. Don't think about it. Don't put in too much effort. You do a chop and you do a chop and you switch them. That's all that you have to do. So I still have the ring that has not been touched. That double bond is still there. It's just not to an oxygen. The Wittig reaction takes the cyclic mechanism and it replaces that with a carbon, and that carbon is bringing some people along with the ride. So there we go. We keep the whole alkyl group intact. And then on the other side is the C6H5 with the 3, the phosphorus that's there. The double bond is still there, but this time it goes to the O. So once more, the game of switcheroo. All right. Now, here's the production of the reaction of the Wittig. So a couple of things that I want to say is that we can, because we're forming alkenes, that's what these are, talk about E and Z stereochemistry. And the rules never go away. The rules of EZ said that the E forms, remember, Z groups are on Z same side. That was cis. Or the E form, which could also be regarded as trans, even though they're different. They're in reference to different things. It's kind of the relationship between the two. When you form these double bonds, the E form will be preferred. And this is something that's not new. This is something that we talked about in Organic Chemistry 1. That has never went away. So when we form the double bonds, if we have a choice, we want to make sure that the groups are further apart from each other so that way they don't invade in each other's space. We don't want that to happen. And the trans formation will allow that to go forward. All right, so trans is always going to be the best option over the cis every single time. All right. Okay, so that's kind of the whole story with the phosphorus ylide and the Wittig. I will say that we can make the phosphonium ylide, and the way that we do that, if we have to do that in-house, is through a substitution reaction that's bimolecular. Again, this is a General Chemistry 1 topic. We can take triphenylphosphine, which I have to handle pretty carefully. The triphenylphosphine can react with an alkyl bromide. It substitutes basically for the bromide, so that's a very good leaving group, and that goes away. And then this begins to form the alkyl phosphorus-containing piece that I would want to use in the Wittig reaction. So from here, what I can then do at this point is bring in an organometallic. And the organometallics we are now familiar with. That was at the beginning of the semester. All right, so this butyl lithium containing group can then be used to basically come in and rip a hydrogen off, and we see the formation of the negatively charged carbon that is here. Keep in mind, organometallics, what do, folks? Organometallics flips the chemistry of the mechanisms of the carbons. So here we form typically carbons that are nucleophiles. And look at what we've done. That's exactly what we need. And that's one of the reasons that we use an organometallic to help us out. All right, so with that said, we are now done with the aldehyde and ketone reaction set. And we have ended this with two specialized reactions called the Wolff-Kishner and the Wittig. So, with that said, wrap it up, review your notes, look at these reactions. They're all very similar. It's just what are the reagents doing? That's the only difference. And good luck on the assignment for the reaction set for the aldehydes and ketones. If you have any questions, you know where I'm at.